Hello everyone, this is a short presentation of our work that was presented at IEEE WCNC 2022. As we know that blockchain is a decentralized ledger of transactions managed by a peer-to-peer network. The decentralized nature of blockchain brings a lot of challenges. First is the high storage costs associated with blockchain. The storage requirements of blockchain always increase with time. The figure shows the size of the Bitcoin's blockchain. Another challenge is the security and the privacy concerns regarding blockchain. The storage costs of blockchain can be broadly divided into two categories. First is the cost of storing the current state, and second is the cost of storing blockchain's historical data. This forms the majority of the storage costs associated with blockchain, and it is the main focus of our current work. The question is, how can we lower the storage costs while maintaining security and decentralization? The answer is to use the power of codes. Recently, many architectures based on coding theory have been proposed to reduce the storage costs associated with blockchain. The list is obviously non-exhaustive, and our work is quite related to the work by Kade, Chung, and Ramchandran. A problem with many of the above works is that they have high bandwidth requirement for repairing the share of a failed node or decoding a particular requested block. Moreover, many of these works need to operate over a field of large size, which limits the scalability. The bandwidth required for decoding a particular requested block becomes an important factor in some applications like healthcare, legal firms, etc. In our work, we have proposed two architectures, namely SPF codes and SPRS codes, which addresses both these problems. Our system model is as follows. At any point of time, we partition all the users into various zones of size m each, and we assign coded data to each zone. We assume that there is an active omniscient adversary which is aware of the transaction data of all blocks, and it can provide malicious data to the users. So how does adversary controls the nodes? In each zone, we impose a constraint that the adversary can read the content of a maximum of Z read-only nodes. It can both read and write the data of maximum of Z read-write nodes, and it can blindly corrupt or jam the data of Z write-only nodes. And we define security parameters capital Z, Z read, and Z write. Now let us discuss how encoding happens in our proposed SPF codes. We encode the blocks in epoch. An epoch is the time required for the chain to grow by L blocks. The encoding process consists of two phases. Fountain codes in the first step, followed by a secret sharing scheme in the next step. L blocks of the blockchain are encoded into K blocks, where L is much larger than K. Now these K fountain coded blocks are encoded into M symbols using the secret sharing scheme, and these M symbols are distributed among M users. The secret sharing scheme is described by these four parameters, where a message of size k over is is encoded into a secret of size m, such that any m-r symbols are sufficient to recover the message, and any zr symbols reveal no information about the message. Now let us discuss the decoding process of our SPF codes. The decoding may happen for three different reasons. First is data reconstruction. In this case, a user requests a particular block of data which is in its access list. Another possible scenario is for node repair. Another possibility is that an entirely new zone has to be created. The decoding process typically happens in two steps. First step involves the decoding of the secret sharing scheme, and the second step involves decoding of the fountain coded blocks. Now, depending upon the situation, we use a combination of good repair, bandwidth, and error correcting properties of the secret sharing scheme in such a way that the communication costs are minimal. Now we will discuss the architecture of our SPRS codes. Our proposed SPRS codes are same as our SPF codes, except with one minor difference that in the encoding phase, we randomly sample k blocks out of L blocks of the blockchain. And as we know that random sampling is a special case of fountain codes where singleton blocks are sampled with probability 1. The following table represents the comparison of the different coding schemes at a constant storage savings of 1000x. As you can see that SPF codes and SPRS codes both have significantly lower bootstrap costs as well as the bandwidth cost. Thank you.